Hello again, guys. Let's go to the next topic. In this topic, we will provide a simple proof of the Pythagoras theorem. This is because we need the Pythagoras theorem to be able to find the length of a line segment or the modulus of line segment. Okay, so we will provide a very simple proof of this. Then, of course, we will remind ourselves of how we determine the length of a horizontal or vertical line segment. Okay, and lastly, we will see how to find the length of any line segment, horizontal, vertical, or oblique. Oblique meaning that it is neither vertical nor horizontal. Okay. Right, so let's move ahead and start by looking at the Pythagoras theorem. Most of us will be familiar with this demonstration here. Okay, I'm hoping you've seen this before. What is this trying to say? Okay, so in general, if we have a right angle triangle with sides A, B, and C as shown, where A and B are the shorter sides and C is the hypotenuse, which is the longer side, the longest side is always opposite to the right angle, then if I formed a square using the smallest side like that, if I form a square with that, then the area of that square, if I add to the area of the square I form with the other shorter side, that area there, if I take that and add them together, Pythagoras says that the sum of these two areas will be the same as the sum of the area made by the larger side as shown. Okay, so in effect, this is what Pythagoras says. So this is the Pythagoras theorem. All right, now we're going to provide a very short, a very simple proof of this, and it goes like this. We will start with this very triangle. So given a triangle, I'm going to place a triangle on this horizontal. Think of that as a ground level. All right, and if I place that triangle there, the triangle has the same sides as we stated earlier. And then what I'm going to do is I'm going to take a copy of that and reorientate it so that side B is on the ground. Right, the triangle will start right there with that edge or that end up there or down there, and side B will now be on the ground with side H being the height. Okay, so if I do that like that, so we still have our A and B like that, then what happens is this angle has to be 90 degrees. Why is that? Because let's say, suppose this angle here was 30 degrees. So if this was 30 degrees, for instance, and this angle here was, say, 60 degrees, let's say this was 60, then clearly, because this triangle is the same as that, it means this one here, this angle is 30 degrees, and that angle there is going to be 60 degrees. Now, if this angle is 30 and that is 60, we know that the total angle around this, okay, angle in a straight line must be 180, and so if this is 60 and that is 30, then 180 minus this 90 leaves us with 90. And so this angle here is going to have to be, has to be 90 degrees, okay? And so what I'm going to do is I'm going to close that distance there. I'm going to join that to form this trapezium, okay? And that angle, as we've said, has to be 90 degrees, which is to say that that orange shape there must be half of a square, okay? And so keeping that in mind, the next thing we want to do is to find, hoping you've understood this. So we took a triangle, mapped it out on this side so that B became the base and A became the height, and then I joined the tip there to the other tip to form basically a trapezium. Okay, so now what's the area of this trapezium? The area of the trapezium is made of the areas of these two triangles plus the area of that half square, the triangle that is a half of a square. Right? Now the area of this triangle is a half times base times height, which is half A times B. Okay, or AB over 2. This is also AB over 2, and this is a half C squared. So this is AB over 2. I can write A times B over 2, or a half AB. This is also AB, A times B over 2. And this is going to be C squared divided by 2. Okay? You can say it is area of the square divided by 2 to give us that triangle there. So I have those those areas there. I want to know what the total area is. So the total area must be a half AB plus a half AB, which is just AB. And then I have to add a half C squared. Okay, like this. So first, the area of the two green triangles there must be twice AB over 2. Okay, so that is 2 times AB over 2, so twice AB over 2, and that is simply AB. Okay, so this plus this is going to give me AB, and the area of the half square is, of course, a half C squared. Okay, area of that green, orange part is C squared over 2, or a half C squared, and so if I added all of them to get the area of my trapezium, then I end up with the area of the three triangles. I'll call that the area of the triangles. The area of the three triangles is the area that I got here for the two green triangles plus that area there, which is just AB plus half C squared. I'm going to take that and put it here. Okay, so that's the area of this shape when we think of it in terms of those triangles. Okay. Next part, of course, is let's think about the triangle, the three triangles as forming a trapezium, and so we are looking for the area of a trapezium, right? All right, so if we think of this purely as a trapezium, that gray shape there, then we know the area of a trapezium is found by taking a half times the sum of parallel sides. So this side here, side B here, and side A here are parallel. So we will do half times the sum of the parallel sides times the perpendicular distance between them. So the perpendicular distance between them is going to be A plus B, but we have the sum of parallel sides. So area of a trapezium is a half multiplied by the sum of the parallel side multiplied by the perpendicular distance between them, which is also referred to as the separation. Now, sum of parallel sides is A plus B, and the separation or the perpendicular distance is also A plus B. So therefore, we have a half times A plus B times A plus B, like that. Okay? If we open this bracket, this is a perfect square, so we get A squared plus 2AB times B squared. I'm going to write this here. So we get, if we open that bracket, we get A squared, because it is a perfect square, 2 times A times B plus B squared. All right? And then we multiply by a half, so the half goes to each of these, so times a half, and you can see this is going to cancel out, and we have a half A squared plus AB plus half B squared, like that, right? So keeping that in mind, let's see. So if we open that bracket, we will end up with a half A squared plus AB plus half B squared, right? And so we have expressed the area of this trapezoidal shape in two ways. One being in terms of the sum of the area of triangles, and now we've found another way of expressing it. So if we think of it in terms of this triangle, that's the expression for the area. If we think of it as a trapezium, so TP for trapezium, TR for triangles. So if we think of it purely as a trapezium, then that is how we find the area. Now, of course, it's the same shape, so these two areas must be the same. And so I'm going to equate the area, the two areas. I'm going to equate them because they are basically the same shape. And so those two areas are the same. Those two expressions must be the same. And so I can equate them like that. All right, and as you can see, AB is appearing on both sides, so I can cancel that out. And if I do so, I'm left with a half A squared plus half B squared on the left-hand side being equal to a half C squared on the right, like that. Okay? Now, if I multiply each term there, if I multiply through by 2, the 2 cancels the half in each of the terms, and I'm left with A squared plus B squared is C squared. So this is a simple proof of the Pythagoras theorem. There is a more I would say, aesthetic proof of the Pythagoras theorem that was provided just this year, I think 3 months ago, by 2 high school students, I think from New Orleans. I have placed a link in the comments section on this proof. You can take a look at it. This proof relies on laws, trigonometric laws, the sine law and the cosine law, and on geometric series, plus a bit of similarity and congruence, basically similarity of shapes, okay? Take a look at that, and hopefully you understand how that proof comes about. It's not difficult, it's actually very, very interesting. Okay. Next, we want to just remind ourselves of how to determine how we found the length of a horizontal line segment as well as that of a vertical line segment. We've done this, so I'm just reminding you of this so that we can move ahead with the next step. We showed that if we are given a line such as that one, then to find the length of that line, so that's a horizontal line and that's a vertical line. To find the length of the line, we need to take the final point. So we are always thinking moving in the positive x direction, and if you're moving in the positive x direction, that's the final point and that's the initial point, although it doesn't really matter. Then you think of the positive y direction, that's the final point and that's the initial point. So if we think like that, then if the line is horizontal, such as the case of AB, then we must take the x coordinate of the final point and subtract the x coordinate of the initial point. In this case, therefore, the length, the modulus of AB must be 2 minus negative 5, like that. 2 minus negative 5. So the value of x at B minus the value of x at A there, we've already talked about this, just a reminder, and that gave us 7. And if the line is vertical, once again, now we are thinking of the y value. So in this case, the length of line DC, notice I've said DC instead of CD because I'm thinking in that direction. So that must be the final point. So in the case of line DC, where the final point is XC and the initial, the YC, because now this is vertical, we are thinking of the y values. So YC minus y of D, there like that. And when we substitute that, we are saying, therefore, it is 5 minus 1 there, right, which is equal to 4. I hope you remember this. We used it in the previous video, and so hopefully you've not lost it yet. Okay, keeping that in mind, we need this if we're going to find the length of any oblique line segment, okay? The modulus of any line segment, meaning can be oblique, can be a line that is going at an angle like that. How do we find the modulus of an oblique line segment, or effectively any line segment, okay? So let's consider the line AB there. So line AB has coordinates, so those are the coordinates of point A, coordinates of point B. Now you should be used to this notation, okay? If we're going to find the length of line AB, we need to make use of our knowledge of the length of line, horizontal line and vertical line, the same ideas we used when we were looking for the coordinates of the midpoint. So we know that moving from point A to point B, we must move horizontally a certain amount of distance, followed by a movement vertically, okay? So we make a point there. So we form some kind of a triangle with a point somewhere here, point C. Now, what are the coordinates of point C? You should be able to see that the x-coordinate of point C is the same as the x-coordinate of point B, which is to say that the x-coordinate here is just xb, all right? Similarly, the y-coordinate of this point must be the same as the y-coordinate of point A. So the coordinates of this point must be xb, ya. I'm going to call that point C. So the coordinates of C must be, the x-coordinate must be xb there, and the y-coordinate must be ya. All right? So if we're going to find the length of this line segment, we need to know, because we are going to use the Pythagoras theorem, we need to know this length horizontal length, and we need to know the vertical length. But we've already determined that the horizontal length, which we shall call A, the vertical length shall be referred to as B, and the hypotenuse will be C. We are looking for AB, which is what we refer to there as C. We symbolize with C. Okay, so AC, which is represented by letter A, must be equal to, let's look at this using a smaller diagram so we can use the space for mathematics. So the length of the side A has to be, it is horizontal, so we must use the x coordinates. Okay, so the horizontal length A must be xb minus xa. Okay, and the vertical height there B must be y, because for vertical we use the y coordinates, must be yb minus ya. Okay, and so if we are going to express, use the Pythagoras theorem, which states that c squared is a squared plus b squared, then c, the value of c that we are looking for, which is the length ab, must be the square root. So we take the square root of both sides, and we get c is the square root of a squared plus b squared. And so all I need to do is to replace the value of a here with xb minus xa, and the value of b with yb minus ya. And so the length of AB, the modulus of AB, which is the length c, must be equal to that expression there. So this is how we determine, this is the formula we use to determine the length of a line segment, or the modulus of a line segment. Okay? Let's see if you have understood this. Let's check your understanding. Here is an example 1. Find the length of each line segment. Okay, we will take a square grid like that. So that square grid there is of unit length, meaning this is 1. So I don't have to put numbers here, you know, that is 1 square, so that is 1, 2, 3, 4, 5, 6, okay, like that. So this is telling you that each square has a side of unit length. All right. We want to find the length of line 1. There's a line 2, and there is a line 3. Please pause the video and try to find these lengths yourself. Okay. Assuming that you've done so, you should be able to find that the length of line 1 is the square root of 40. So you should find the square root of 40. I put that into my calculator, and I find that to be approximately 6.32 to 3 significant figures. If you are an IB student, you should know that we will always require answers, decimal answers, to be given to 3 significant figures unless otherwise stated. Okay? So if you have to change that from it, this is called an exact value. If you have to approximate it, we will usually approximate to 3 significant figures like that. All right. What about line 2? If you did this correctly, line 2 should have a square root of 89, which is in turn 9.43 to 3 significant figures. And line 3 will be the square root of 45, which can be expressed as 3 root 5. Okay, reducing that using method of surds that we've learned before. And so if you find that on a calculator, it should give you 6.71. It was 6.708, something like that, which to 3 significant figures is 6.71. Okay, so that is how you, if you did this correctly, you should get that as the answer. All right, let's look at another example. Okay, example 2. Find the length of each line segment whose endpoints are given. So we are told what the endpoints are. We are no longer given a graph. So we only have our endpoints. What is the length of line, or the modulus or the length of line AB? If you've done, please pause the video and try this out yourself. And then, assuming that you have done so, the answer for the length of side AB should be equal to the square root of 125, okay, which is the same as 5 root 5, which, if you express it to 3 significant figures, is going to be about 11.2. Okay, what about PQ? If you did PQ correctly, you should get the square root of 130, which is approximately 11.4 to 3 significant figures. And line CD, the length of CD is the square root of 242, which is the same as 11 root 2, which when you multiply, I think gives us about 15.6. Okay, so these are the answers that you get if you have done that correctly. Please try it out. Write down something in the comment section if you are getting something different, and I will do a video solving this question. All right, I believe this is the last one. A line segment PQ is 15 centimeters long, given that the end P has coordinates negative a, negative 3, and the end Q has coordinates 6a. Find the value of a. This is a nice examination type question. Please pause the video and try it out, and then see the solution as I have figured it out. Okay? Right. And so there is our line. I'm going to have the lower end there will be P and the upper end will be Q. And just like we reasoned before, I could use the formula directly, but I want us to go ahead and do it in steps, just like the way we derived the formula. And so there is the horizontal part and the vertical part. So I can form that right angle triangle there. So I need to know the length of the horizontal side and the length of the vertical side. Looking at this point, what are the coordinates of this point? The coordinates must be, the x coordinate must be 6 and the y coordinate must be negative 3. Okay, like that. And therefore, if this side is A and that is B, and our side C is, we know what our side C is, it is 15. Okay, if that's the case, and we are looking for, I think I should have used different symbols here or that, but I think it doesn't matter. I should have used different symbol because then we are confusing this A with this A. They are not the same. Maybe we should use M there. It doesn't. Let's just move ahead and see. And so the length of side A here, the length of this bit, must be 6 minus negative A. So 6, the final point minus the initial point. So 6 subtract negative A. 6 minus negative A is actually 6 plus A. And so A squared then must be equal to 6 plus A squared. Okay, since the length of this side here is 6 minus negative A. 6 minus negative A is positive A. So 6 plus A squared. Similarly, B squared must be equal to A minus negative 3, and A minus negative 3 is positive 3. So A plus 3, and therefore B squared is A plus 3 squared. Yeah, so first of all, before I go to B, we can open this bracket, of course. So 6 plus A squared gives us, this is a perfect square, so we can open directly. That is going to be 6 squared plus twice 6 times A, that is 12A, plus A squared, right? And so that gives us 36 plus 12A plus A squared. B squared is A, or just B alone is A, B. So we said A here was, this is the value of A is 6 plus A, and the value of B here is A plus 3. Okay, so that's the value of A. And so if we are going to find the value of B, then we can write that B squared is A plus 3 squared. A plus 3 squared. One moment. So that's A plus 3 squared. And if we open that bracket, this becomes A squared plus twice A times 3, that is 6A, and then plus 3 squared, which is 9. So we end up with A squared plus 6A plus 9, like that. Okay? All right, so that is A squared and B squared. So now we know A squared, we know B squared. Now the value of C is 15, so C squared must be 225, 15 squared. And so we can write using Pythagoras theorem, Okay, c squared must be 15 squared, so 225 must be equal to a squared plus b squared. That means we are adding all this together. So let's add the like terms. 36 plus 9 is going to be 45. All right. So we have 45 when we add this and that. 6a, 12a adds to 6a, and that is 18a. Okay, so plus 18a there. And then we have a squared and a squared there, so we have 2a squared. If we simplify that and move everything to one side, we form a quadratic equation, and we don't need to work this our head off with this. It's a simple step. If you already know how to solve quadratic equation, this is straightforward. Otherwise, you can also place it in a calculator, and it should give you two answers. That is a, the values of a we are talking about here, a is 6, or a is going to be negative 15. Okay, and so these are the potential values for a. So if a is 6, then the coordinates of point P must be -6, -3, and 6, 6. Okay, so -6, -3, and 6, 6. On the other hand, if a is negative 15, then putting negative 15 here, we get 15, -3. So this becomes positive 15, -3, and 6, -15. Okay, so those are two potential values of the unknown letter there, a. Okay, sorry that we had to confuse with our a from Pythagoras theorem there, but I'm hoping that you got this. All right, this brings us to the end of our discussion on how to find the modulus of a line segment and all that related information. I hope if you did not know where Pythagoras theorem came from, I hope you had an opportunity to see a simple proof there and that it made sense. Please look at the proof by those young high school girls onto the Pythagoras theorem, which is it's quite interesting. Okay, assuming you got this right. Please like the video and consider subscribing if you've not already done so. That way, when we post any video, you are not left out. Okay? I'll see you in the very next video. Thank you.